So I'd like to welcome everybody. This is a collaborative effort with Dana Visalli, the naturalist, the Met naturalist. We want to thank him so much for doing this. This is the second series, and we're just so thrilled. I mean, this is so fun to learn all this wonderful history and nice diversion. And my name is Deirdre Cassidy. I'm the program manager for Met at Home. And so I think I'll just continue to admit people and we'll hand it over to Dana. Thank you.
Greetings, everyone. I actually can't tell who is present. There's what I see are just a first few people who are showing up. But thank you so much for participating. And Big History is a good story. I don't know to what degree. I mean, I'm sure it varies from person to person. Any connection you can to it. I do want to mention the endless resources under that title, Big History, and two good ones are there's a Wikipedia page on Big History, which just goes on and on because Big History goes on, and there is a program called the Big History Project. So you can Google the Big History Project, and there's actually a long course that you can take for free. It would be the same material. So those are two resources. Big History is I'd say a new way to talk about actually evolution, the evolution of the universe and the evolution of the Earth and life on Earth. It's just kind of a user-friendly way to refer to this big story. And it was originated, that name was originated by a guy named David Christian, who is Australian. And if you go to Big History Project, I think Bill Gates actually funded the Big History Project, that webpage and the instruction. And Dave Christian features prominently there. He's a very good educator and speaker. And he feels that a deeper understanding of our deep history will help us to going forward in our lives and on the planet. A friend, Greg Student, who is actually on, that's Aaron Student's dad, for those of you who live here, is on the board of the Cleveland Museum of Natural History. And he said something I thought was instructive a while ago. They found a new dinosaur fossil, a new species. And the people on the board were all excited about this new dinosaur fossil. And Greg's response was, so what? We don't need another dinosaur. We know about dinosaurs. What we need to know is how to live on the planet. It's a good point. Maybe it's not categorically correct, but that question, so what, is worthwhile. And so Big History, so what? It's hard to answer. And these science stories are so full of facts. You know, there's four programs here with this naturalist, with Big History program, and a lot of scientific, it's not boring, but there's a lot of material. And what I think the best result is actually a heightened state of awareness about the world around us. I don't think we're trying to become physicists or biologists. It's just a reminder that we live in a remarkable place. And to reinforce that, I want to mention there's a good YouTube, and some of you will know this man's name, most of you may not. This man's name is David Steindl Rast. He's a Benedictine monk. So if you Google David Rast, you can leave the Steindl out. David Rast, A Good Day. It's just 5 minutes on gratitude. And he starts by saying, open your eyes and be thankful that you have eyes to open. It's like, oh yeah, I forgot about that. We forget. So I recommend those. I want to mention the Met Naturalist because the next issue is issue number 100. It comes out in December, and it will have an article. It has a big history orientation, and it will have that issue. Will have an issue on Goldilocks Effects, which we're going to be talking about. And Goldilocks Effect is that somehow, strangely, everything on Earth is just right in a really very dangerous universe for life to persist. And we'll talk a little more about that. So if you're interested in the Met Naturalist, if you Google that, you go to the webpage, and actually the current issue is posted there and other such stuff. So I've shown this particular picture several times. I like to tell people it's a picture of the Milky Way. But with a little understanding of space, we can't take a picture of the Milky Way because it's 100,000 light years across. So it would take 150,000 light years, traveling the speed of light, to get out of the Milky Way to get a picture. So this is probably the Andromeda galaxy. But the interesting thing is, we didn't know, humanity, Homo sapiens did not know that we lived in a galaxy. We didn't know that the lights in the sky were stars until about 100 years ago. We didn't know that there were other galaxies until about 90 years ago. We are really just learning about the universe and the planet that we live in. I have a favorite quote. Oh yeah, Carl Sagan. Carl Sagan says, "We humans are like a newborn baby left on the doorstep with no note explaining who it is, the baby in the basket, where it came from, or what its hereditary cargo might be." You know, we're just find ourselves here and we don't know what's going on. I think big history helps. Big history isn't going to answer the great pressing question, what's it all about? But big history helps. So what is it all about? This is a cute cartoon about evolution, and there is another part to this cartoon to come forth here, but this is a fish coming out of the water. What's it thinking about? Eat, survive, reproduce. Amphibian turning into a reptile, turning into a primate. Most of life is concerned about eat, survive, reproduce, and this new creature has appeared called Homo sapiens and stands up on its hind feet, and it does wonder what it's all about. I think it can be argued that Homo sapiens is something different on the planet. The way the human mind works is something different. It's contemplative and abstract mind is, we're part of the biological world, but we also have a different sort of assignment. Well, the effort to understand our place on the planet has been ongoing and has resulted in the evolution, the appearance of not one religion, but innumerable religions. There are currently calculated to be 6,000 religions on the planet, and they're based largely on believing things that we can't quite see, but the way the human mind works, we can think anything. We can make the abstract thought about anything, and then have a belief in that. And I think that, you know, we can see that happening this morning in certain ways. So it wasn't that. What are some of our beliefs that actually probably mostly we don't believe in these things anymore? It was widely believed by Western civilization that the earth was flat, and that people, if you sailed out into the Atlantic Ocean, you'd go off the edge. God made the world in 6 days. That is in the Bible, isn't it? I think it's in the Bible. There was a calculation made from Genesis, from going through Genesis, by a minister, that the earth was 6,000 years old, and they had a date, a year and a date when the earth was made. So this was widely believed. In fact, when Darwin came out with his book, The Origin of Species, in 1859, and said life has evolved, humanity has evolved, and it's going to take a lot of time, and 6,000 years is not enough. One of the biggest hang points was that people believed the world was only 6,000 years old. Now we believe that the planet is 4.5 billion years old, or we think it is. But I would say we don't know for sure. The scientific evidence is it's very old, but that's a long time ago, hard to know for sure. This comes up more in this slideshow that it was widely believed that the sun revolved around the earth, because I think it's animal nature and it's human nature to be self-centered. And one of our projects is to make a little space in that center for more living things than own lives and our own family say. We're concerned about our own DNA. It's just common. It's not anybody's fault. It's just not functioning so well now to be self-centered on the planet. Anyhow, part of that was we wanted everything revolving around us. And the belief was very strongly held that the sun revolved around the earth. Stars were just holes in a glass dome. I mean, that's what they look like. You don't look like stars, you know. And that you could get to heaven if you paid enough money. That was widely believed. And this is a little random, which out of A Green History of the World, the human excrement should be thrown out on the street for health reasons. In medieval Europe, that's, you know, people went to the bathroom in chamber pots, and what did they do with the excrement? They threw it out the window in the morning. It was dangerous to walk down the street. If you thought you had to get it out of the house, throwing it in streams was very highly thought of. This is the nature of belief as compared to actual information that's functional based on reality. This is, I think, an Aristotelian from Aristotle image of the earth, of the universe, from the long-lived concept that the earth was the center of the universe. The sun revolves around the earth, and actually it looks like the sun revolves around the earth. It comes up in the east, goes across the sky, and goes down in the west. That's the way it looks. It's taken a long time to learn that this is not the case, and it was a long and difficult journey. This is a guy named Giordano Bruno. So you remember Copernicus, who was one of the first astronomers, was able to observe the universe, the planets, and he came to understand that the Earth was not at the center, but that the sun was at the center. But he was afraid to publish because he was afraid he'd be killed by the Catholic Church if he published his book. And he didn't publish it until he was on his deathbed in 1543. So they couldn't kill him because he was dying. Well, people took up his cause. Giordano Bruno was one who took up his cause, and he knew from the evidence from Copernicus and others, he could see that it was a sun-centered solar system, not Earth-centered. And he insisted this was the case, and he was arrested by the Catholic Church and imprisoned for 8 years and tortured for 8 years. He would not recant. He just said, the truth is the truth. I can't say anything but the truth. And he was burned at the stake in 1600. And you'll remember at least the bare outline of Galileo, also just not too long after, I think 1613, he had made a telescope and he could see the Earth was not the center of the solar system. The Catholic Church accused him of, gosh, it's a great term, just wild heresy, and he was condemned to house arrest for the rest of his life. Point being, the truth is often not very popular, and the truth can be dangerous. So the truth in terms of what we understand about the scientific story is that the universe is on a journey. And I think that's the biggest part of the big history story. There's something going on. The universe is not static. It's on a journey, and we are a part of that journey. So big history has these themes of increasing complexity. The universe has grown and keep increasingly complex over time. We're going to talk more about these. Things emerge that did not previously appear. So it has this theme of emergence, which is, as I put in a note when I was putting out the word about big history, it's the most, I don't even want to say hopeful, it's the most encouraging aspect of the story of the universe. New things are constantly emerging. One of the new things is human intelligence. It shouldn't shock anyone to say that human intelligence has not been perfected. It's a work in progress. It's a work in progress. And there is no reason that we could not grow more ecologically, what I call ecologically intelligent, so that we know how to live on the planet. We didn't recognize the phenomenon of ecology. The word was new in about 1865. It basically means interrelationship, that everything is related to everything else and dependent on other aspects of life. You know, that's what we still don't know very well, but we know it a bit. And I think it's growing in us. So themes, complexity, emergence, Goldilocks effect, and major thresholds. the universe has gone through major thresholds which are identifiable. So increasing complexity, I just pulled up a picture. That's a hydrogen atom. A hydrogen atom has one electron and one proton. You can't get much more simple than a hydrogen atom. And in the early universe, it was almost all hydrogen. Now there are 92 elements. That's increasing complexity. And from those elements have come things like planets. There were no planets because there were no elements, only hydrogen. You can't make a planet out of hydrogen. It's just trying to illustrate the fact that indeed the universe is getting more complex. So this also illustrates that. Hydrogen atom, the early universe was, I think it was 75% hydrogen from what we understand. Nobody was there. Science has deduced this from evidence. And 25% helium, which has 2 protons and 2 electrons. It's the second most simple of the 92 elements. So how do you get from hydrogen to? There are now estimated to be 2 trillion galaxies. 2 trillion galaxies. We didn't even know there was one galaxy 100 years ago. So even our understanding is an emergent property of the universe. And how do you get from the lower picture? Those are bacteria, my favorite picture of bacteria. How do you get from the most simple forms of life, these very simple single cells that are so tiny you can't even see them with I have a microscope sitting right here, goes up to 800 power. You can't see bacteria, they're so small. That was the size of early life. Now there's 10 to 20 million species on the planet. And I think I have, pulling up one more picture here down in the lower right-hand corner, a blue whale. The largest organism that has ever lived on the planet, alive today, weighs 100 tons, 200,000 pounds. And that's from bacteria. That has evolved from. So increasing complexity, we're just saying, it's a fact. The universe is on a journey, and it's identifiable. It can be seen that this is true. Emergence. New things are constantly emerging in the universe. It's a dynamic, creative process. We don't tend to think of it that way or see it that way. It looks rather static to us, except for the weather. But no, that's not the case. Things are always changing. So here we have something is going to emerge. We have 2 elements. We start with, in the picture here, there's hydrogen, there's 2 hydrogens, there's 1 oxygen. And there's hydrogen's a gas, oxygen is a gas. You combine them into H2O and you get water. It's the emergent property of the universe. Not only that, there was no oxygen. In the early universe, there was only hydrogen and helium. Where did oxygen come from? We'll talk about that. The Goldilocks effect. It's a wonderful story, and I'm looking forward to writing that article. I have taken notes. I probably have 50 things written down that are Goldilocks effects, and I'll bet there are thousands if you really went into it. Aspects of life on Earth, aspects of the dynamics of the Earth that are just right for life to persist. One of the obvious ones is that the Earth is in what is called the habitable zone. It's in green there on that slide, and a little bracket there to show that the Earth is within the habitable zone. It's the surface of the sun is something like 7,000 degrees Fahrenheit. You don't want to get too close. I mean, unless you can come up with a life form that can live at 7,000 degrees, but none are known. Space is, I forget the temperature, but it's well below zero, like 400 degrees below zero in space. You really don't want to be out in space. Everything, it's just like Goldilocks porridge. Earth is just right. And it's just right in many ways. A couple other aspects that I can think of. So you could not put solid matter together without atoms, and the atoms, the elements, are made up of protons, electrons, and neutrons. Protons are 2,000 times larger than electrons. They have exactly the same charge. They're opposite charges, positive and negative, but they're exactly the same. If they weren't exactly the same, the universe would not hold together. No solid elements would ever form. It's a Goldilocks effect. And where did it come from? It's inscrutable. I don't think there's any way to answer that question. The universe passes through thresholds. So the Big Bang is a strange phenomenon. The Big Bang, the story of the Big Bang is that everything appeared from nothing in a single instant. Well, so there's a biologist named Terence McKenna who says, well, if you believe that, I have a bridge over in Brooklyn that I'd like to sell you. He says there's nothing more improbable. There's nothing less believable than everything appeared from nothing. And if you think about it, that's true. Everything appeared from nothing. It's not comprehensible. But the evidence, because the universe is expanding, which has only been known since 1927, 90 years, the universe is expanding. That means if you run it backwards, it all goes back to a point. There is evidence that it exploded. It's incomprehensible as far as I'm concerned. I don't know if there are physicists who think they understand the Big Bang. But it was also a threshold. If there was nothing and then there's everything, you have to admit that's a big threshold. This is the big history story, and it's true as far as we know. There was a bang, but there were no stars. There was just hydrogen and helium. Stars, I would say most stars are fusing helium into larger elements, primarily helium, which has 2 protons instead of 1 proton. But at first, there was just hydrogen and some helium expanding out into space. And what actually seems to have occurred is that the force of gravity took hold, and as the cosmologist Brian Swim likes to say, one hydrogen atom took an interest in another hydrogen atom and started to attract that hydrogen atom to itself. And it might have become H2, it'll be a molecule then, 2 hydrogen atoms. It's bigger, it has more gravity, because gravity is based on mass and distance. So it would attract more hydrogen atoms. So this gas cloud started to condense into thick clouds of hydrogen that increasingly pulled the hydrogen in and condensed until there was so much friction from hydrogen atoms smashing into one another and so much pressure that it ignited. And that means that the hydrogen started breaking down the bonds of the atom and forming helium, fusing into helium. And I'll tell you the big history story, a lot of it, until at least you get to living things, is incomprehensible. And what I'm thinking of at the moment is, I keep checking this online, the story about the sun. So our sun is fusing hydrogen into helium. How much hydrogen is it fusing? 600 million tons a second. Now, how comprehensible is that? It's totally incomprehensible. I told my neighbor, I read that the other day online, and I said, I'm worried that the sun will burn out and my solar panels will then be useless. It's a joke, because everything will be useless if the sun burns out. It's supposed to burn for another 4 or 5 billion years. It's just right. Our sun is just right. By the way, the sun is just right. If it were any, 1/1000th of the sun's energy reaches the earth. If 2 billionths reach the earth, we'd roast. It's just right. It's 93 million miles from the earth, or the earth is 93 miles from the sun. If we were probably 83 million miles, we'd roast. If we were 100 million miles, we'd freeze. Goldilocks took care of everything. These are thresholds. There was no universe. The universe appeared. We don't know how. The stars ignite. It becomes somewhat understandable to the scientific community in the way I described it. Gravity pulled the hydrogen together and smashed it so tightly that it ignited and starts fusing hydrogen into helium. Well, that's a new element. Now there's 2 elements where there was 1. There are 92 elements. They were all created by the universe. Half of them were created by fusion in stars, and the other half were created by supernova explosions. We'll talk a little more about that. You can't have planets without elements. You can't make a planet out of hydrogen and helium. You have to have silicon, iron, magnesium, oxygen. Those are the main elements of the earth. They didn't exist until they were created in this creative process of the universe that is our universe to live in. It's not a static place. We are part of a magnificent evolutionary process. Life appears. Well, science keeps trying to figure out how life appeared. I put life in the same category as the Big Bang. Nobody understands where life came from. You know, experiments are done. They've been able to create organic molecules, which are carbon-based molecules, where they didn't exist, but no one's come close to creating a living thing. So I'm following the outline of David Christian and the many thinkers that have made this wonderful, drawn out this wonderful story of big history, the evolution of the universe and life. But I have put in my own material. So I put in where David Christian goes is, I guess it would be number 6, is the evolution of humans. I just bumped him down one. I put in photosynthesis. I mean, it is hard to grasp how important photosynthesis is on the planet. Photosynthesis is the capacity of living things to capture sunlight and store the energy that is arriving from the sun as chemical energy that can then be used by life. It turns the energy of this arriving from the sun, that 1/1000th of the sun's energy, into sugar. That's what plants do. That's what photosynthesis is. Plants and certain cyanobacteria. It's incalculably important, photosynthesis. So I put it 6th. And then Homo sapiens. And it's not just Homo sapiens, but that we're unusual. Abstract thought, which I'm not sure, abstract thought. One of the primary characteristics, I think, of Homo sapiens, of our species, we think all the time. We are making symbolic images in our head of the world outside of us. And as we talked about before, they aren't necessarily accurate. And so what David Christian has is agriculture. Agriculture is a big deal. I don't deny that, but I think abstract thought is more important. So I put it in there. I'm just telling you, different people have different ideas. And so he had modern industrial society, also a very big deal. And that's the cause of this huge impact on the planet that we're having. I think I would put as the 8th major stage in the evolution of the universe, actually, is the appearance of intelligence, which I think is not fully appeared yet, and ecology, which just means a comprehension of interrelatedness. Nobody has to be right here. These are just ideas. The Big Bang, from nothing to everything. They say the universe is 14 billion years old. There is evidence that it all started out as a singularity. It's completely incomprehensible. Star formation, this is could be actually a picture of a hydrogen gas cloud starting to contract because gravity is pulling it together. And that is how stars form. I'm going to look, well, not yet. I do need to look at my notes. So this is an interesting aspect. I went and got this slide. I showed this in the natural history program 2 months ago, and I went back and got it out of that program because it's really a critical, I just put it in this morning. It's easy to understand, but it's a critical aspect of the universe and an additional mystery. And that is how orderly the universe is. I wish I had my numbers on there, but there's so that's a hydrogen atom, 1 proton and 1 electron. But from the orderly nature of the universe, that electron is in something that chemists call a shell or an orbital. And you've heard those terms. It's a shell. But that shell holds 2 electrons. The first shell holds 2 electrons. And so a hydrogen atom is not completely at ease being a solitary hydrogen atom. Now, I'm consciously anthropomorphizing here, turning a hydrogen atom into a little person that's thinking. But the fact is, I mean, it's not a thinker, but in terms of the electrical charge of that very basic element, there is a electrical attraction to join with another atom so it can fill that first shell. And it'll very readily join with another hydrogen atom, and they share electrons, and both of them then have 2 electrons in the shell. And the big mystery for the human mind is, where does this deep, intense orderliness come from? Because this electrical attraction to fill the orbitals, the shells, is what causes the inevitable increase in complexity of the elements and molecules and the solid material of the planet. So here's oxygen. Oxygen has 8 electrons, but the first 2 have to go in the first shell and then it's full. That leaves 6 for the second shell, but the second shell holds 8. So oxygen is faced with the same electrical distress that the hydrogen atom was. It wants 2 more electrons. So what becomes almost inevitable? It wants 2 more electrons to fill its shell, because we live in an intensely orderly universe in spite of yesterday's elections. Little joke. And so what do you end up with? You end up with oxygen inevitably sharing 2 electrons with other elements, here hydrogen. And so oxygen now has 8 electrons in its outer shell, so it's electrically satisfied. Hydrogen has 2 in its more simple shell. And what do you get? Water. Water is an inevitable evolutionary product of the orderliness of the universe. It's just fantastic. And so I have these couple of quotes here. Belgian biochemist Christian de Duve, who's won the Nobel Prize in Medicine, says, life may be an obligatory manifestation of matter. He's just referring to this process that matter spontaneously constructs itself. The oxygen and hydrogen, because of this electrical charge, they can spontaneously go together. Well, that process continues through a spectrum of elements and more shells that want more electrons. So then Ilya Prigogine, who won a Nobel Prize in Chemistry, says, the statistical probability that the most precisely harmonized reactions that typify living organisms would be generated by accident is 0. It's the intensity of the orderliness of life is so profoundly refined. It can't be an accident. It's the nature of the universe, and the universe is on a journey, and we're part of that journey. Now, we are not talking about God. We're talking about this profound orderliness. We don't know where it came from. And I've told kids in class, you know, if you have beliefs in God, there's plenty of room for God here. You can insert your God, but this is factual material, this deep, profound order of the universe. So what do we have here? I forget. Are we going to make more water? We're making helium. So how are we going to get more elements? We started out with mostly hydrogen. Well, look at how easy, I think, how simple physics is. If you combine 2 hydrogens, hydrogen has 2 protons and 2 electrons. Sometimes it has no neutrons, mysteriously. I don't quite get that. All the other elements have neutrons as well. But if you combine 2 hydrogen atoms, if you can smash them together, break down the resistance, the electrical repulsion, probably from the electrons, which are both negative and repel one another, under enough heat and pressure, you're going to have 2 protons in the nucleus, helium. How hard is that to understand? It's not hard. 1 + 1 is 2. So a very fascinating fact that I read is E = mc². That's not the fact I read. You remember that. That's energy equals mass times the speed of light squared. There's a lot of energy in mass. That's the point of Einstein's equation. The sun, as I said, is fusing 600, I forget, what did I say, million or billion? I'm going to go with million. 600 million tons of, you can look it up on Google, 600 million tons of hydrogen a second. It's producing 596 tons of hydrogen. It's missing 4 tons. That's true. I mean, as far as we know. What happened to the 4 tons? That's where the energy of the sun is coming from. It's the mass that was in the hydrogen atoms is being turned into energy and radiating out from the sun. You know, it's like a magic show. So the human body is 65% oxygen. Well, there was no oxygen. That's my point here in this slide. 18% carbon, there was no carbon. Nitrogen, calcium. These things didn't exist. There was only hydrogen and a little bit of helium. Where did they come from? Well, we talked about this, how to build a universe. Hydrogen, 1 proton, helium, 2, carbon, 6. All you need to do is keep smashing atoms. They just have more protons. Nitrogen 7 protons, oxygen 8 protons. You know, it goes up. There's 92. It's very orderly. There's a number 9, 10, 11, 12, 13, 14, 15, 16. But it takes tremendous heat and pressure to overcome the electrical repulsion of the electrons. Where are we going to get tremendous heat and pressure? We need some kind of huge press. That press turns out to be the stars. The stars, and I do need to find these numbers because they were so impressive. So we need a lot of pressure and heat to fuse any element into another element. I looked it up. So the average temperature on the surface of the Earth is 58 degrees. The surface pressure is 15 pounds per square inch. You know, that comes to bear on us a bit, but we're used to it, so it doesn't bother us. So that was 58 degrees Fahrenheit on Earth. The center of the sun is 27 million degrees Fahrenheit. And the pressure is 4 trillion pounds per square inch. We think. No one's been there. Well, that's what it takes. These are just gigantic, unimaginably large creations that are pulled together. Still, all that mass is attracting itself to the center of the star, creating this tremendous heat and pressure that becomes enough to start fusing elements. This is some of the elements. They're not all here, but you recognize the images as being part of the periodic table. So the top one, hydrogen, it's a given. It was given by the mystery of the universe in the Big Bang, hydrogen and helium. Our star is a red giant star, the second entry, the second line. And certain elements, it has enough heat and pressure at, what did I say, 27 million degrees and 4 trillion pounds. You only get to iron. It doesn't say that there. Well, it has iron in the hot blue star. See, they're larger elements. It takes more and more pressure and more heat to create these elements. And you get in a hot blue star, which like Regal in Orion, which comes up every middle of the night right now, that bright blue star in Orion's, is it in his foot or in his belt? I think it's in his foot. It's a bright blue star. It's blue. You look at it, it's bright blue. It's a hotter star. It's a larger star. It burns more rapidly. It'll burn out much more quickly than our star, but it's hotter and more pressure. It creates more elements, and you get up to iron, but then it stops. To get the rest, they were made in supernova explosions. Certain stars, when they stop being able to fuse, that fusion energy is resisting the gravity. And when the fusion stops, the star collapses on itself. And these are super large stars. I forget, at least 10 times larger than our star, maybe 100 times larger. They collapse upon themselves, and the gravity becomes so great they explode into supernova explosions, and the rest of the elements are made. We don't need to understand this completely just to know that it's a remarkable process, and it's the source of our lives. If there had not been supernova explosions prior to the construction of the Earth's solar system and the planet, life would not be possible on Earth. Supernova explosion. So I have this little information here. I'll say a star the mass 10 times that of the sun, says the sun is 300,000 times larger than the Earth. A supernova is 3 million times larger than the Earth. And it says 180 billion degrees. We got up to 27 million degrees in the sun. Now we're at 180. So you end up being able to fuse. You can fuse elements that don't want to be fused, like uranium, which is radioactive. It has 92 protons. They're all positively charged. It doesn't want to hold together, and it slowly falls apart, called radioactive decay. That was fused in the supernova explosion. So now we're into our solar system. We have a sun that's fusing hydrogen, 600 million tons, that sounds right this time around, per second, which is unbelievable. The Earth is just debris in orbit around the sun that consolidated into a solid planet. It's leftover space debris. That might sound unlikely, but it did not take very much debris. And I know the next picture shows the size of the Earth relative to the size of the sun. It's nothing. It's just nothing. So there's a picture there. You can see the Earth labeled and the arrow. So it's just a little bit of solid material. 4.5 billion years ago. So the universe was already 10 billion years old and had time to create the other elements, which then got incorporated into the solar system when the Earth's sun formed 4.5 billion years ago. I'm going to bring up the other part of this. So that's the Earth. The Earth is tilted in relation to the plane of the sun at 23. It's tilted at 23 degrees to the plane of the sun. It should be at 90 degrees, just because of the way it would have formed in its orbit. In this debris aggregating would have been in orbit around the sun, and it would have been formed at 90 degrees to the sun. But the Earth is not 90 degrees. It's tilted 23 degrees away or towards the sun. It varies as the Earth orbits the sun. Why? And the most widely accepted explanation at this time is that a planetesimal, a small planet, smashed into the Earth soon after the Earth aggregated, like 4.4 billion years ago, and knocked it over. It was already in orbit around the sun, and it was hit by a smaller planet. It blew part of the Earth's crust out into space, which went into orbit around the Earth and became the moon. That is the accepted scientific story. The moon came from somewhere. The tilt came from somewhere. You cannot believe that story, but you'll have to come up with your own to explain. Well, that is a major, major Goldilocks effect. And that's an interesting thing about our universe, that some of the worst news, I mean, we had an article in the Naturalist a number of years ago, have you thanked your catastrophes today? Because catastrophes often are turned into Goldilocks effects, which make enhanced life possible. So what am I talking about? For one thing, if the Earth wasn't tilted at 23 degrees, there would be no seasons, and there would be no moon, there would be no tides. And it's thought that the Earth blew a portion of the Earth's crust into space, as I said, became the moon. If the Earth's crust was any thicker, there would be no plate tectonics. If there was no plate tectonics, which recycles the nutrients necessary for life that run in the rivers down to the sea, they subduct under the continents, and they come back out of volcanoes. Because of plate tectonics, life would have ground to a halt. But the planet recycles all of the Earth's elements that go into the ocean back out of the mid-oceanic ridge, rift, and volcanoes. This is partly because we were hit by a planetesimal. It's a Goldilocks phenomenon. This is a cartoon. It's Primordial Soup, made to look like Campbell's soup. And it's just to illustrate life appeared, and we don't know how. And, you know, it is said that life appeared out of the primordial soup. The elements, it was dynamic. There was a lot going on Earth. There were very strong winds. The moon was a lot closer to the Earth. The tides were much, much stronger. A lot of electricity in the air. And, you know, that's the best science can do, to explain how these elements, which had their own orderliness, as we've talked about, built in, somehow managed to appear as life forms that are able to eat, survive, and reproduce. And we don't know how that happened. But it's interesting to me, you know, we talk about maybe animals as being sentient, as being, especially the higher up, the more recently evolved animals, with our sense receptors and our mobility, our ability to perceive the world and respond to the world is pretty well developed, and we call it sentience. You know, but it was interesting to me to realize that all life is sentient. All life perceives its environment and responds to it. Bacteria, the simplest life forms on the planet, will move towards positive stimulation and away from negative stimulation. It'll move towards food and away from enemies. It's sentient. All life perceives its earthly environment and responds to it. This is a Venus flytrap flower, or I guess they're flowers, you know? Maybe they aren't flowers. But, you know, if a fly goes in there, it hits those hairs, and it has to hit two hairs. I don't know quite what that's about, but it has to hit. It won't trigger. It won't. That trap will not close if the fly hits one hair. But when it's a second hair, it catches that fly, and the Venus flytrap, as you know, it digests the fly and uses the nutrients in the fly. It's a carnivore, carnivorous plant. Quite remarkable. So here's the biosphere. This is a graphic representation of the biosphere on the planet. And look what dominates. I was surprised. This is a fairly recent report. I could send you the link. It's got some other cool, easy to understand graphics. So gigatons are billion tons. It said there are 600 billion tons. Once again, million and billion. It must be billion. Tons of life on the planet. Most of the life on the planet is plants. And most of those are trees. We don't tend to appreciate trees for being the dominant life forms that they are, but that's the case. There are 6 kingdoms of life, generally speaking, generally agreed. Some people divide it a much finer, and those are listed there. And there's a 7th entry there, viruses. We're very aware of viruses these days, but they are not considered a kingdom of life because they have no life of their own. They have no life of their own. Oh. But, I think it's arguable whether viruses are alive or not. Anyhow, it's interesting to see the breakdown. And animals are down there, down there at 2 gigatons. But see, animals are dependent on plants. Animals cannot capture the energy of the sun and turn it into food. That's the specialty of plants. Yeah, probably enough said about that. So how do they do that? It's quite a process, quite a stunning process. You know this, but we're just reviewing it. Plants take carbon dioxide in out of the atmosphere. They draw water up from their roots. They split the hydrogen off of the oxygen, which was proven in 1940. It was wondered before that where the oxygen came from because there's oxygen in carbon dioxide. The hydrogen is attached to the carbon dioxide and you get an emergent property, you get sugar. CH2 is the most basic formula for sugar, or C6H12O6 is glucose, which is actually what plants make, but I simplified it. And the oxygen, O2, it's a molecule of 2 oxygen atoms because I'm sure that fills that outer shell that we talked about that wants 8 electrons. And the oxygen is released into the atmosphere. And that's, of course, what we breathe. Well, why do we breathe that? I mean, I've been asking people, mostly nobody can answer that question. We're not as curious as we could be. So I was asking the kids at school, why do we breathe? Well, nobody knows why. I mean, we do know the information exists. And the actual answer is to break that sugar molecule back apart, that CH2 that's in the sugar, and harvest the energy of the sun that was stored there by photosynthesis. So photosynthesis is a magic show. And how much of each? How much water? How much hydrogen? Plants are 90% carbon dioxide. I think that's underappreciated. And the reason is, the next I have it coming up here, the biosphere, those 600 million tons, I'm going back to million, I'm sorry, I can't remember, million or billion, of that massive amount of living tissue on the planet, it's appearing out of the atmosphere. 90% is coming out of the atmosphere. This is true. It's unbelievable, at least it's magical thinking. It's the same as the Big Bang and the appearance of life. It's just hard to comprehend. So I'm jumping here to humanity, and I don't even know what threshold. Maybe this is emergence. We're talking about life emerging and new things emerging. Humanity uses its brain, and it is an unusually large brain, and we'll talk about that certainly in the last of the 4 programs. The brain in hominids has grown extremely rapidly over several million years until we live this sort of symbolic life where we're trying to understand the planet, but we're also creating symbols of who we are. And so that rock on the left is called the Makapanskat pebble, which I like to say I was able to buy for $1,000 so that I could use it in my shows, but it's probably worth 10. I just made this out of clay. This is my effort to make the Makapanskat pebble. So this Makapanskat pebble was found in a cave used by Australopithecus, pre-Homo, 3 million years old species, Australopithecus afarensis, that lived before our genus, Homo, ever appeared on the planet. It was in a cave. It was not a native rock in the cave. Something brought it into the cave. There were signs that the Australopithecines had used the cave, and it's thought to be the first sign of abstract thought on the planet, the first evidence, because an Australopithecine saw this rock and he thought it looked like his wife, and he brought it into the cave and showed it to her. Said, "Darling." No, who knows? But that's what happened. And perhaps a better illustration, but much more recently evolved, are beads. These beads are about 100,000 years old, carved by Homo sapiens, found in a cave in Africa. They're shells with holes punched in them so they could be strung on a string and hung around the neck. Why? What other animal makes beads and hangs them around their neck? Well, a bowerbird, actually. But it's symbolic thinking. We're turning the physical world into a symbolic world, for better and for worse. And is this better or is this worse? The power of symbolic thought. And we are now near the end of this talk. I lost track of time, and hopefully we're okay. But this whole thing about competition and identification is pure symbolism. What do we have to do with the Seattle Seahawks? If they win, how does that improve our self-esteem? It's purely symbolic. It's purely imaginary. It's mythical thinking. These are clans in Scotland. And it's interesting that they erased England. Scotland doesn't really want to be a part of England. They just took off the English part of the island. But this is symbolic thought. These people, they have the capacity to by degrees, to think about the being on the planet, the meaning of being on the planet, and they're finding their meaning through symbolic thought, through identity with the people around them. But what does that result in? It results in these major divisions of humanity, when in fact, not only are all humans part of the same evolutionary process and family, but we're dependent on thousands of other organisms, ecology, for our lives. So this symbolic thought has its questionable qualities. And how accurate is it? This identity is based on the power of self, the importance of our self-identity. So that drove this belief that the Earth was the center of the universe. And this map is a picture of Europe, probably drawn, I forget actually, but maybe 1400. Well, that little sea is the Mediterranean. Mediterranean, if you define it, break it down from the Latin, means middle of the earth, Mediterranean. They thought they were the middle of the earth. Everybody thinks they're the middle of the earth, but it turns out to not be true. It's just not accurate. So symbolic thinking is valuable, but it's hazardous. So this is a little project to test our own capacity. Are we seeing the world the way it is, or are we seeing it the way we're programmed? So when I show this slide, we won't know how well this plays out. You're just supposed to read the card and read the message he has for you. I'm sure that's long enough. So how many of you think it says you will pick the red card? Show of hands. I can't see you. That one person. So it does not say you will pick the red card. I can see Deirdre's checking it out. It says you will pick the red card. There's two thes. But our mind interprets the world for us. You don't need two thes. Our mind just wipes it out. It's right there on the screen, but we can't see it. Because of our conditioning, we learn to see the world the way we think is the best for our survival, eat, survive, reproduce. And the point is we don't see the world accurately. And that's valuable information, It should, it could invoke humility. So, sorry. It's just an interesting graphic about reality, ecological reality. The one on the left, we have, the general human sense that we are the apex of the evolutionary process. So it shows a man at the top and a woman just a little lower. And, there's a lot of that going on. And the other animals and life forms are interesting, but not as interesting as we are. And on the right is a more ecological context. And I think that is what is going to save us, is waking up to ecological reality, that we are part of this magnificent ecological matrix and evolutionary journey. That it's our job is to wake up to it. And it's hard to do. I have a hard time with it. I have a hard time with students. So ethics, you could call it morality. I like the word ethics. The universe started with hydrogen. Where did ethics come from? Where did the idea of right and wrong come from? Animals are not concerned about right and wrong. I mean, the proof is, let's see, I think in the ecology program I showed a picture of a mountain lady slipper. It's a trap pollinator. That flower tricks animals into pollinating it. It doesn't give them anything. It just sort of lies. That's fine in nature. But now there's this phenomenon of ethics. I mean, the question is, what is going on? Well, it's an emergent universe. We never know what's next. Ethics is a powerful force. It hasn't taken over the planet. So it's just so cute. Calvin was trying to decide whether to lie or not. And he says, I can't decide whether to do the right thing and fail or the wrong thing and succeed. Well, that's the price of ethics, isn't it? The evolutionary journey, if the 4.8 billion years of life were condensed into a year, life appeared on April 8th. So I circled the 8 there. Photosynthesis, critical to life on the planet. So there was life before, but it was very simple. It was just harvesting the energy in some odd sulfur molecules. July 1st, halfway through the existence of the planet, halfway through the imaginary month, photosynthesis appears. Life emerges onto land in December. For most of the history of the Earth, there was no life on land. Now, by far, the largest portion of life, I would say 95% of life is on land. But there was no life on land for most of history. It's a journey. Mammals appeared late in December, and humans appeared on the last day. And it's a journey. It's not over. It's not really December 31st. We have many more months. So to me, it's delightful to wake up to the fact that we are part of this enormous journey and we have a part to play. And it may be a small part. This is a picture of the Earth from 2.5 billion years out in space, a billion miles out in space, taken by a satellite. And because you can't see it, I put an arrow on it. And this is used in Carl Sagan's little video. You can watch his video on YouTube. It's a pretty powerful video called A Pale Blue Dot. And so it puts today's drama into perspective. All of every individual's drama, all of every country's drama takes place, as Carl Sagan said, in a mote of dust floating in a sunbeam. So don't worry, be happy. And everyday miracles, this is our planet, couldn't be more beautiful. And I just wanted to, and I like that image, human. But the story there is that we are not on the Earth. We are of the Earth. I think it's actually indisputable. Somehow life emerged from this dynamic planet and has led to the emergence of mammals and Homo sapiens. We are of the Earth. This is our home. It's a beautiful reality. And if you want to appreciate that, you can look up David Steindelrast's little 5-minute video of the day. It's just a gratitude. I downloaded it. I like it so much. So I think that's the end of the show. Hope you all survived in good form. Well, it's 10 o'clock. That's pretty good. I couldn't see the clock until I erased the video.